Okay. All right. So let's talk about longitudinal waves now. Longitudinal waves are harder to measure, but they're important to understand because I'm going to relate mechanical waves to sound, and sound is a longitudinal wave. So the definition, the key difference is this word right here, parallel. In a longitudinal wave, a wave will move in the same direction as the particle motion. Okay, they'll be parallel. The particle motion is parallel to the wave motion, the direction that the wave moves. So I can show you that easily with, well, I can show it to you here. See, notice the transverse wave, the particles go up and down. But here in the longitudinal waves, the particles move side to side, and so does the wave. It moves to the side. Here's another one. You can see the wave fronts here, the pulses are moving to the right. But if you look at an individual particle, it moves to the right and the left. So the direction of the particle and the wave pulse are always parallel. That's what makes this a longitudinal or compression wave. Okay, so that's what I just said about particle motion and wave motion. They're parallel. All right. The amplitude would be related to the volume. If this was a sound wave, if we were talking about amplitude of a sound wave, that would be how loud the sound was. Okay, but if we were to try to measure it somehow, I don't know how we would do this practically, but it would be the distance from the equilibrium position of the medium to a compression or rarefaction. Okay, this is a compression, a place of compression, and rarefaction, a place of expansion. Okay, and these compressions would be your wave pulses. Okay, compression is the region where the medium is compressed. That's your actual wave, that's your disturbance that you sent through, and your rarefaction is the region where the particles are spread out. All right. So we still need to talk about wavelength, period, and frequency. And the thing about this is, just like a transverse wave, these only apply to longitudinal waves that are periodic, like this one, where the pulses are sent out in regular intervals of time. So there's no wavelength, frequency, or period to speak of for a single pulse. It doesn't exist. These values only exist for periodic longitudinal waves. Okay, and the ideas are the same. The wavelength is measured a little differently. The wavelength is the distance from compression to compression now. Okay, but the frequency and period are pretty much the same ideas. The equations are the same. I'm not even going to rewrite them. They're the exact same as what we saw up here. But the frequency, now that's the number of pulses that pass a certain point. So that's the number of compressions that pass a certain point now. And period is the amount of time it takes one of those compressions, the entire compressions from start to end, to pass a certain point. Okay, so the ideas of frequency and period are the same. It's just that instead of peaks and troughs traveling, we have compressions and rarefactions traveling through the medium. Okay. All of the sources that I had online are here, and this whole document will be posted to Canvas for you to look through and for you to explore these extra resources if you would like. Hope y'all enjoyed it. Have a good one.